Time is much more than the simple ticking of a clock on your wall. It is the invisible, fundamental framework that underpins our entire technological society. Think about the Global Positioning System, or GPS, that guides your car or helps you find a nearby cafe with your phone. This incredible system relies on a network of satellites, each carrying an extremely precise clock. The satellites send signals to your device, and by calculating the tiny differences in the arrival times of these signals, your phone can pinpoint your exact location on Earth. Without clocks that are accurate to within billionths of a second, GPS navigation would simply fail, leading to errors of many kilometers. This need for precision extends far beyond just finding our way around. The world's financial markets, where billions of pounds are traded in fractions of a second, depend on synchronized time to ensure fairness and prevent fraud. Every transaction is time-stamped, creating a verifiable record of when it occurred. The internet itself, the very backbone of our digital lives, needs accurate time to function correctly. From sending an email to securing online data, everything relies on computer systems being perfectly synchronized. It's a silent, constant pulse that keeps our connected world running smoothly. A pulse generated by some of the most sophisticated devices ever built, atomic clocks. For decades, the undisputed champion of timekeeping has been the cesium atomic clock. It is the official timekeeper for our planet. The international definition of 1 second is based on the behavior of cesium, 133 atoms. Inside these clocks, a cloud of cesium atoms is exposed to a specific frequency of microwave radiation. When the frequency is just right, it causes the electrons within the atoms to jump between two very specific energy levels. The clock effectively counts these atomic ticks. To be precise, 1 second is officially defined as the time it takes for exactly 9,192,631,770 of these oscillations to occur. This standard has served us brilliantly for over half a century. These remarkable clocks are the reason we have a stable and consistent global timescale, known as Coordinated Universal Time, or UTC. National laboratories around the world operate their own cesium clocks and contribute their data to maintain this global average. It's an extraordinary collaborative effort that ensures when it's 3 p.m. in London, it is precisely synchronized with the corresponding time in Tokyo or New York, accounting for time zones. This stability is crucial for everything from international air travel to scientific experiments that span the globe. But as incredible as cesium clocks are, science is now on the verge of something even better. Imagine a clock so precise that it would not lose or gain a single second over the entire age of the universe. This isn't science fiction, this is the reality of optical atomic clocks. While cesium clocks rely on microwave frequencies to measure their atomic ticks, optical clocks use something much faster: laser light. The frequency of visible light is about 100,000 times higher than that of microwaves. This means that in the same 1 second interval, an optical clock can count vastly more ticks. It's like having a ruler with much finer markings. You can simply measure things with far greater precision, and in this case, the thing we are measuring is time itself. These new generation clocks use different types of atoms, such as strontium or ytterbium. These atoms are carefully trapped by laser beams and cooled to temperatures just a fraction of a degree above absolute zero. At these incredibly cold temperatures, the atoms are almost perfectly still, which removes many of the tiny errors that can affect their measurement. A finely tuned laser is then shone on these trapped atoms. The laser's frequency is adjusted until it perfectly matches the natural frequency required to make the atom's electrons jump to a higher energy state. This stable, ultra-high frequency of the laser light becomes the new, incredibly fast pendulum for our clock. The result is a staggering improvement in accuracy. Where the best cesium clocks might be off by 1 second every 300 million years, an optical clock could run for 15 billion years and still be accurate to within a second. This leap in precision is so profound that it opens up entirely new possibilities. We can measure time so finely that we can detect the effects of Einstein's theory of general relativity on a human scale. For example, an optical clock will tick ever so slightly slower if you lower it by just a few centimeters, because it is deeper within Earth's gravitational field. This effect is minuscule, but optical clocks can measure it. This incredible sensitivity makes optical clocks more than just better timekeepers. They are exquisite sensors. They can detect tiny changes in gravity, which could one day be used to monitor volcanic activity or search for underground deposits of water or minerals. Their stability and accuracy are pushing the boundaries of what is possible in measurement science. But before we can harness this power and officially redefine the second based on these new clocks, the global scientific community needed to be absolutely certain that they all agreed with one another, no matter where they were in the world. This led to an unprecedented international collaboration. In science, a new standard can only be adopted when it is proven to be robust, reliable, and repeatable. To build this confidence in optical clocks, an extraordinary experiment was conducted in the first half of 2025. It involved linking 10 of the world's most advanced optical clocks located in laboratories across 6 different countries: the UK, France, Germany, Italy, Finland, and Japan. The goal was to compare their ticks simultaneously to see if they agreed. It was a monumental undertaking, a kind of global timekeeping summit designed to test the readiness of these new technologies for the most important job in metrology, defining the second. To compare these clocks, scientists needed to establish links that were themselves incredibly precise. Otherwise, the connection would introduce more errors than the clocks themselves. 2 main methods were used. For the European labs in France, Germany, and Italy, dedicated optical fiber links were established. These are not your everyday internet cables. They are specialized networks capable of transmitting the stable frequency of one clock directly to another with almost no loss of precision. This method allowed for comparisons that were about 100 times more accurate than any other technique, providing a gold standard measurement of how well the clocks performed relative to each other. For the clocks that were further apart, such as connecting Europe to labs in Finland and Japan, the scientists had to rely on satellite links. Using signals similar to GPS, they could transfer timing information over vast distances. While this method is less precise than the dedicated fiber links, it was essential for creating a truly global network and ensuring that all the major players in the field could participate in this critical comparison. The campaign involved conducting 38 different frequency comparisons between the various clocks, giving the researchers a rich and complex data set to analyze and cross-reference, a vital step toward a new definition of time. The findings from this huge international effort, published in June 2025, were a major breakthrough. The project successfully demonstrated that a distributed international network of optical clocks could be operated and compared with remarkable consistency. As Rachel Godin from the UK's National Physical Laboratory noted, the scale of the campaign was unprecedented and essential for moving forward. The results provided crucial information that will help the international community decide which type of optical clock, whether strontium, ytterbium, or another, will form the basis of the future SI second. It was a huge step forward, but the work is not yet complete. Despite the success of the 2025 comparison, there are still challenges to overcome before the world can officially adopt a new definition for the second. One of the main hurdles is reducing the measurement uncertainty even further. While the optical clocks themselves are incredibly precise, the links used to compare them, especially the satellite links, introduce small errors. The goal is to get the uncertainty of these comparisons down to less than 5 parts in 10 to the power of 18. This is a fantastically small number, but it is necessary to fully take advantage of the clock's intrinsic performance. Achieving this will likely require expanding the high-precision optical fiber network across greater distances. Another key challenge is ensuring long-term reliability. A new global standard for time cannot be based on a technology that is just a laboratory curiosity. The optical clocks must prove they can operate continuously and reliably for long periods, consistently contributing their data to the world's timekeeping authorities. This means moving them from experimental setups to robust operational instruments. The multi-clock, multi-link approach of the recent campaign was invaluable here, as it helped scientists identify and diagnose unexpected inconsistencies in some results, which, as Helen Margolis of NPL explained, will ultimately help improve the performance of the next generation of clocks. Once these hurdles are cleared, a redefinition of the second will be on the horizon. This new definition will have profound implications far beyond just keeping time. A more precise second will immediately improve technologies that we already rely on, such as GPS, allowing for even more accurate positioning for everything from autonomous vehicles to advanced navigation systems. It will also enhance the speed and security of our communication networks and financial systems. It's an upgrade to the very foundation of our technological infrastructure, one that will enable innovations we can't yet fully imagine. Perhaps most exciting are the possibilities for fundamental science. A network of synchronized optical clocks spread across the globe would essentially create a planet-sized sensor. Scientists could use it to perform new tests of Einstein's theory of relativity with unprecedented accuracy. They could use it to search for the elusive dark matter that is thought to make up most of the universe's mass, by looking for tiny, telltale fluctuations in time as the Earth moves through it. We might even be able to test whether the fundamental constants of nature are truly constant. By learning to measure time better, we are opening a new window onto the universe and its deepest secrets.